So far we discussed the stable properties, but our discussion was mostly informal because we didn't define a topology in the space of differentiable maps. So it was not clear what it means for two differentiable maps to be close. We use the concept of homotopy, but that's not very satisfactory because an homotopy between two maps is not unique. So in order to make that discussion more formal and our results more powerful, we are going to introduce in this lecture two topologies in the space of differentiable maps. So we have already studied stable properties of the set of differentiable maps. As I said, an important point was describing when two maps are close. And in order to do that, we used homotopies, right? Now we will consider a more general approach. We will define two topologies in the set of differentiable maps, right? First of all, we are going to remind what a topology is. So a topology defined in a set S is a family of subsets of S, such that the family contains the empty set and the set S, such that too the union of elements of the family still belongs to the family, any union, finite or infinite, countable or uncountable, doesn't matter. And finally, the intersection of two elements of the family still belongs to the family, which implies immediately that finite intersections of elements of the family still belong to the family. Under these conditions, we say that F is a topology and the elements of the family are called open sets of the topology. Okay? So this is the basic definition of a topology defined in a set S. But many times we don't provide all the open sets in a topology. We give a topology in different ways that do not involve specifying every possible open set. And in this way, we get to the definition of base of open sets. We say that B is a base of a topology defined in S if B is a family of subsets of S, if the union of the elements of B is equal to S, and finally, if given any two sets in the family and a point that belongs to the intersection of them, there exists another set in the family that contains the point X and is contained in the intersection. Okay? And we can actually define a topology just by considering unions of sets in the family B. That would define a topology, and you can check out that that's the case, okay? As I said, the open sets of the topology are the unions of elements of the family. Something that we get in this case is that a base of open sets do not necessarily contain all the open sets of the topology. For instance, if we consider in Rn, let's consider the usual topology for the Euclidean space Rn, right? And consider the balls, for instance, of radius of center x and radius epsilon, where x belongs to Rn and epsilon is positive. That is a base of the topology, even if, of course, it does not contain every open set in the topology because not every open set is a ball. But every open set is a union of balls. And indeed, when we have a point that belongs to the intersection of two balls, there is a third ball, that contains the point and it's containing the intersection of the other two. So yeah, that the definition checks out. So in general, providing a base can be simpler than giving all the open sets of the topology because yeah, we are just giving a subset of the open sets of the topology that can be easier to describe. Okay, so please check out that this defines a topology. That if we have a base of open sets and we consider the unions of elements in the family, that is always a topology defined in S. Right. We can also consider a subbase of a topology. So consider a family C of subsets of X, and now we are going to define a family B whose elements are finite intersections of elements in C union S. We consider also the possibility of, this is just to ensure that S is going to be one of the sets, one of the open sets of the topology. Then in such a case, B is the base of a topology F, and we say that C is a subbase of F. This is very good because here we don't have any condition. For every family of subsets, C, we can build a base B, and once we have the base B, we obtain by considering unions all the open sets of the topology. So this is a very convenient way of giving a topology, just providing a subbase of such a topology. Let us define now the weak topology on the set of CR maps from M to N, where M and N are CR manifolds. So let us define the weak topology on the set of CR maps from M to N, where M and N are CR manifolds. Assume at first, because it's simpler, that R is finite, and let us define the weak topology on CRMN, on the set of CR maps from M to N. This weak topology is also called CR compact open topology. And one way of defining a topology is by defining a subbase. So let's do that. We are going to fix some data. We are going to fix first a differentiable map, a CR map from M to N. Then we are going to fix a local chart phi, define a local chart of M, a local chart psi of N, a compact subset K contained in the domain of the local chart phi and whose image by F is contained in the domain of the local chart psi, and also let's consider a positive real number epsilon. Okay. And what we want is defining this set over here, which is just, by definition, the set of CR maps G from M to N, such that the image by G of the compact set K is still contained in W, and when we consider the difference of the local expressions of F and G in the local charts phi and psi, what we get is that the norm of these kth derivatives is smaller than epsilon. What is this norm? It's the norm that you prefer. For instance, you could consider the supremum over phi of k, over the point x, sorry, of all derivatives of order k. That works. The particular norm that we're going to use is not really that important because norms in Euclidean spaces are all equivalent, so different norms are going to define the same topology. So what the particular norm are we using here is not really a big deal. So in this way, we define a subbasis. The sets in the subbase are exactly the sets of this form, okay? And We're just saying that the derivatives of order up to R of J are very close to the derivatives up to R of F. And indeed, how close is given by this inequality, so by the inequality that is written here. Okay, why we need to consider this definition that a priori looks a little bit technical? Okay, here probably the two most important elements, besides obviously F, are the compact set K and epsilon. We are actually comparing the derivatives of order up to R of F and G in K, right? And epsilon is the scale. We are requiring them to be of norm smaller than epsilon. But obviously, in order to consider these derivatives, we need to work in Euclidean spaces. And so it is natural to consider local charts, because otherwise it is not clear what the derivative of order k of f is. So in order to put this in the framework of Euclidean spaces, we need to consider local charts. And why are we considering here a compact set of U? Because local charts are not necessarily well behaved. I mean, its derivatives, for instance, when we approach the points of the boundary. So in order to work in a geometrical framework and not introduce artificial problems when we approach the boundary of our local charts, we need to consider compact subsets of the domain of the first local chart. Okay, in this way, our definition is going to be geometrical. So this is the definition of a subbase of the weak topology, and we saw that given a subbase, there is always one topology that in our case is just going to be the weak topology for the space of CR maps from M to N. A neighborhood of F is just a subset of this space of differentiable maps containing a finite intersection of sets of this form. Of course, not necessarily the first component over here is going to be always equal to F, but it is possible to see that indeed if you have an intersection of subbasic neighborhoods that contains F, there is a smaller intersection of subbasic neighborhoods of this form, that contains your first finite intersection. So in order to obtain the neighborhoods of F, we just need to consider sets of differentiable maps that contain finite intersections of sets of this form. Yeah, you can check this out. So we know how a neighborhood of a differentiable map is going to be. Okay, let's work in the simplest case in which R is equal to 0. So we consider a sequence of continuous maps from M to M, and we want to know when does this sequence converge to another continuous map F, right? And what happens is that if you consider the expression of Fn in local charts, what we need is something of this kind. We need that if we consider K, which is contained in the domain of definition of a local chart, okay, of M, what we need is that for any given epsilon, this expression holds for n big enough and every x. So we have, if you want, that the supremum this of x and phi of k is smaller than epsilon for all n sufficiently big, right? But in particular, since this has to work for every epsilon, this implies that if it implies the following, okay. If Fn converges to F in the weak topology, right, then Fn converge uniformly to F in any compact subset contained in the domain of a local chart. Okay, in some compact sets that are related to local charts. The issue is, since every compact set can be actually written as a finite union of sets in this form, it is very, very easy to prove that if Fn converges to F in the weak topology, then Fn converge uniformly to F in K for every compact subset K of M. Okay? In any compact subset K of M. But if you have now that if the sequence Fn converge uniformly to F in any compact set, then in particular these expressions tend to zero when n tends to infinity, this expression over here. No matter what is the compact set K, the local chart phi or psi, is always going to go to zero when n tends to infinity. So what we are saying is that if we fixed any subbasic neighborhood of F, all the elements of the sequence are going to be in that subbasic neighborhood from some moment on. So in particular, that implies that Fn converges to F in the weak topology. So this condition over here, that it was indeed a necessary condition to have weak convergence of the sequence Fn to F, is also a sufficient condition, okay? So Fn converges to F in the weak topology if and only if Fn converge uniformly to F in every compact subset. And so what you can tell, so what we are saying, so that it is clear, is that Fn converge to F in the weak topology if and only if Fn converge uniformly to F on every compact subset K of M. And so you can see why the weak topology is called weak, because indeed it does not say much of what happens, for instance, when we go to infinity. It specifies pretty well, in the case of conversion of sequences, what happens in compact sets. But for instance, the rate of convergence in these compact sets could be slower and slower when we are going to infinity. And that's the kind of thing that the weak topology is not going to be able of dealing with. So if we actually want to understand the behavior of differentiable maps in outside of every compact set, what we can call the neighborhood of infinity, we need to consider another topology. The weak topology is not going to be enough to deal with this kind of problems, right? So this is what I said. Fn converges to F in the weak topology if and only if we have uniform convergence of Fn to F in any compact subset of M, and the weak topology does not control the behavior of maps at infinity. Something that we can now realize is that the Whitney approximation theorem, we discussed the approximation result, how the Whitney embedding theorem can be understood as an approximation result. And now we are at the point in which we can make that statement more rigorous. So in the Whitney embedding theorem, we have a compact CR manifold in which R was greater or equal than 2. And what we say is that embeddings are dense for the weak topology. Embeddings are dense among the maps, the CR maps from M to RQ. If Q is greater or equal than 2 times M plus 1, where small m is the dimension of big M. And immersions are dense for the weak topology in the space of CR maps from M to RQ whenever Q is greater or equal than 2 times M. Let's see the situation with embeddings. All right, so we have a map F from M to RQ, which is CR. This map is not necessarily an embedding. What we want to see is that there is an embedding that is close to F, okay? But we know, because of the Whitney embedding theorem, that there exists an embedding from M to R 2 times the small m plus 1. And that's an embedding. As a consequence of that, we can actually find a map H from M to RQ plus 2 times m plus 1 that sends the point X to Fx Gx. And that it is also an embedding because G is an embedding. Okay? Now, what we have is that our map F is the composition of H and pi. And pi is the orthogonal projection in R Q times 0. But what we proved when we were discussing the Whitney approximation theorem is that we can find another projection, pi prime, as close to pi as we want, such that the composition of H and pi prime is still an embedding, okay? Since H is an embedding, we can find this projection that makes the composition still an embedding. Here, we don't have any problem saying close because we are talking about linear maps. And so these linear maps are matrices, and we are working in Euclidean spaces of finite dimension, yeah, we consider the usual topologies in those spaces. And of course, what we see is that when pi prime converges to p, the derivatives of the composition of h and pi prime converge to the derivatives of h and pi. So in this way, what we're going to have is that that in every neighborhood of f for the weak topology, we are always going to find an embedding. And so the set of embeddings is indeed dense. Okay, in the case of immersions, we just need that Q is greater or equal than 2 times M. But it's very interesting. So the Whitney embedding theorem can be actually interpreted as a theorem that says that in certain spaces of differentiable maps, embeddings are dense or immersions. So far, we defined the weak topology on the space of CR differentiable maps. Let's define now the strong topology. So again, assume that R is finite, and let's define a base of the CR strong, also fine or Whitney topology on the space of CR maps from M to M. So first, consider a locally finite set of local charts of M. Locally finite means here that the family of the UIs is locally finite. It's just that. And now consider a family of compact subsets of M such that Ki is contained in Ui for any I in lambda in our set of indexes. At that point, we define a family of local charts of the target space N such that the image by some f that we are going to fix, as we did in the definition of the subbasic neighborhoods for the weak topology, such that for this fixed f, the image of Ki is contained in Wi. And now for every index, we are going to consider a positive real number. So we have some data. We have fixed map F, fixed CR map F. We have here a family, locally finite family of local charts of M, a family of local charts of N, a family of compact subsets, such that Ki is contained in Ui for every I, and a family of positive real numbers. And in those conditions, we are going to define this set as just the set of maps G, CR maps G, such that we have this expression over here. We consider the local expression of G and F in the local charts phi I and psi I, and we compare the derivatives of order f to r in the image of Ki by phi I. And we require that this norm, whatever it is, whatever norm we chose, is smaller than epsilon I for every x in phi I of Ki. Okay? And for every e in our index set, and for every derivative from order 0 up to order r. So what is the main difference with the weak topology? In the weak topology, we actually consider conditions on compact sets. Okay, since we were considering a subbase, the base could be obtained by considering finite intersections. So in the weak topology, we are considering conditions of this kind in a finite family of compact sets. Whereas in here, we are considering conditions, inequalities like this, in a family of compact sets that can be infinite. The unique condition that we are requiring, besides obviously these compatibility conditions with local charts, is that our family of compact sets is locally finite, because the family of the UIs is locally finite, and since the KIs are contained in the UIs, such a family is also locally finite. So we are considering proximity conditions on different compact sets, but on a family of compact sets that is just locally finite. Okay. So an issue is that in the definition of the weak and strong topology, we have local charts, and maybe this definition makes more difficult to understand these concepts from a geometrical point of view. So it could be interesting to obtain a simpler base for the strong topology of CR maps from Rm to Rm, because in there we don't have to consider local charts. Okay, we are already dealing with Euclidean spaces. And what we can see is that we can consider a continuous function epsilon from Rm to the positive real numbers, and a set n f epsilon that is the set of differentiable of CR maps G, such that the norm of the difference of the k derivative of f and the k derivative of G is smaller than epsilon of x for every x in Rn and every k from 0 to R. And what happens is that indeed this family that we are considering over here, in which f is just a CR map from Rm to Rn, and epsilon is a continuous function from Rm to the positive real numbers, here should be m, this is a base of open sets of the topology. So it explains quite well what the difference is between the weak and the strong topology. In order to have for a sequence, for instance, if R is equal 0, for a sequence of continuous functions, in order to converge, we need just uniform convergence in compact sets, right? But in order to have convergence for the strong topology, we need something much stronger, because we need that from some moment on, the difference of Fn and F has to be smaller than epsilon x for every x. And we are actually controlling the rate of convergence. We are controlling how the rate evolves when our points tend to infinity. So in particular, convergence in the strong topology is more difficult to obtain than convergence in the weak topology, okay? And the strong topology has many more open sets than the weak topology. If you want, in the weak topology, we control what happens in compact sets. Here, we are controlling what happens in all the manifolds. So we could actually consider, for instance, consider here a function in a compact set, and when we get away from the compact set, we can consider functions that are higher and higher. And in that way, it's easy to see that every open set in the weak topology is an open set in the strong topology, but the strong topology has many more open sets, right? Indeed, something that it is possible to check out is that every open set for the CR topology is also an open set for the CR+1 topology, right? These topologies that we are defining, of course, what I mean is that if you consider an open set in the CR topology and you intersect it with the functions of class CR+1, then it is an open set in the CR+1 topology, okay? So in this way, we can use this information to define topologies on the set of C-infinity maps from M to N. We have these maps over here from the C-infinity maps to the CR maps. It's just inclusion. Every map sent to itself. In other words, the C-infinity maps are a subspace of the CR maps. And here we have topology. It can be either the weak or the strong topology. And we can give to the C-infinity maps the topology of subspace, in which actually the open sets here are just the intersection of the open sets in here with the C-infinity maps. So in that way, we get a CR topology for the C-infinity maps for every app. And these topologies are bigger and bigger. Every open set for the CR topology in the C-infinity maps is an open set for the CR+1 topology in the C-infinity maps. So we can consider the union of all these open sets. And in that way, we are going to obtain, you can check out this, a topology on the set of C-infinity maps. If we consider here always for the CR maps the weak topology and the union of the weak topologies for the space of C-infinity maps, we obtain the weak C-infinity topology. And if we consider in here the strong topologies and here the union of all the family of open sets, which is the union of all the families of open sets for the CR topologies defined in this space over here, we obtain the strong topology for the C-infinity maps. Okay, so in this way we have weak and strong topologies for C-infinity maps from M to N. We can also define weak and strong topologies on the set of real analytic maps from M to N, of course, if M and N are real analytic manifolds. Because we just do something similar. We have weak and strong topologies defined in the set of C-infinity maps, and every real analytic map C-infinity. So we can give to the set of real analytic maps the topology of subspace. If we consider in C-infinity maps the strong topology, the topology of subspace for the real for the space of real analytic maps is going to be I don't know what I said, for the strong is going to be the strong topology in the set of real analytic maps. And if we consider here the weak topology, we obtain as a topology of subspace the weak topology for the space of real analytic maps. Okay, so in this way we have weak and strong topologies for all these spaces of maps. In this lecture, we defined two topologies in the set of differentiable maps, namely the weak and the strong topologies. In next lecture, we are going to see that some of the distinguished properties that we considered in the set of differentiable maps, as for instance, being an immersion or being a submersion, are indeed stable for the strong topology. Thank you for your attention.